As an introduction to algebraic structures, we first study the integers. First, some definitions. We say let a and b be integers, and also assume that b is not 0. Then we say b divides a if there exists an integer c such that a is equal to b times c. And we say if this is true, then we write b divides a like this. So b bar a means b divides a, and we say b is a divisor of a. Okay. Let's see a simple example. 3 divides 6. According to this definition, there should be some integer such that 6 is equal to 3 times c. So of course this c is 2 in this case. And 4 does not divide 6. So in this case we write like this. So for any integer c, we cannot satisfy this equation. This never holds as long as c is an integer. Therefore 4 does not divide 6. And 10 has trivial divisors, plus minus 1, plus minus 10. So these are trivial because 1 divides anything and any integers. Negative 1 also divides any integers. And that the integer itself divides itself. And negative of that integer also divides itself. So these are called trivial divisors. And other than the trivial divisors, there are plus minus 2 and plus minus 5. These are non-trivial divisors of 10. Let's prove a simple lemma. Let a, b, c be integers, and b is non-zero and c is non-zero. Then if b divides a, b divides a, and c divides b, then c divides a. Okay. So let's prove this. So since b divides a, there exists some integer such that a is equal to b times d. And since c divides b, there exists some integer, let's say e, such that b is equal to c times e. Okay. Now substitute this b into here. Therefore, a is equal to c e times d, which is equal to c times e times d. So therefore, of course e times d is an integer. So this means therefore c divides a. C is a divisor of a. And we are done. So in other words, divisibility divisibility is transitive. So if this holds, then this holds. And it is easy to find some examples. For example, 25 divides 175, and 175, you should try this, divides 700. So according to the lemma, 25 divides 700. Okay. In fact, 700 is 25 times 28. Let's try to enumerate all the divisors of, let's see, 18. So divisors of 18 are plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 9, and plus minus 18. Out of which plus minus 1 and plus minus 18 are, of course, trivial divisors. But anyway, we always, if you want to enumerate all divisors, we always have to write plus minus, plus minus, plus minus, and that is a little bit cumbersome. So, but we don't have to do this actually because this is trivial. In fact, we have the following lemma. Let's say a, b are, suppose a, b are non-zero integers. Then the following four statements are equivalent. 1, b divides a. 2, b divides negative a. 3, negative b divides a. And 4, negative b divides negative a. So when we say these are equivalent, that means if this is true, 1 is true, then 2 and 3 and 4, they are also true, and vice versa. And vice versa means if this 2 is true, then 1 is true, and 3 is true, and 4 is true. If 3 is true, then 2 is true, 1 is true, and 4 is true, and so on. And I think this is almost trivial, but let us prove some of them. So let's take 1 and 2. Let's try to prove these two are equivalent. Equivalent means if 1 holds, then 2 holds. And if 2 holds, then 1 holds. So we need to prove both directions. Okay? So that's what we do to prove it. So suppose, first let's see, let's try to prove this part first. Okay, so that means suppose, first we assume b divides a. Then this means according to the definition, there exists some integer c such that a is equal to b times c. Okay. Then multiply both sides by negative 1, we have minus a equals to minus b times c, which is equal to b times minus c. So now we have this. Therefore, b is a divisor of negative a. So this is done. But we have to prove the opposite direction. So suppose, but actually we can go just backwards, right? But anyway, so next we prove the opposite direction, converse. So suppose b divides negative a. Then there exists some integer c such that negative a is equal to b times c. Maybe we should use some other symbol just to avoid confusion. So instead of c, let's use d here. Okay. Then multiply both sides by negative 1. We have a equals to negative b times d, which is equal to b times negative d. Of course, negative d is an integer. Therefore, b divides a. And we are done. So all other equivalencies can be proved similarly. And you should try that. Now, because of this lemma, we don't have to deal with plus minus, plus minus, plus minus. We only have to talk about positive divisors, because if there's a positive divisor, there is a corresponding negative divisor. So it's trivial. So we just talk about, from now on, we just talk about positive divisors, unless otherwise stated. Okay. Now let's define prime numbers. So if an integer p, which is strictly positive and not equal to 1, it's said to be a prime number, or just simply prime, just say prime. If it has only trivial divisors. So that means only 1, or p itself, can divide p. And all other numbers, p, if p is not prime, we say p is composite, or composite number, if p is not prime. So all integers are divided into two classes. One is prime, the other is composite. Let's see some examples of prime numbers. 2 is a prime number, 3 is prime, 4 is not prime, but 5, 7, 11, 13, they are primes. And actually there are infinitely many prime numbers. And on the other hand, for example, 4 is not prime because it's 2 times 2. So 2 is not a trivial divisor, so 4 is not a prime number. And 6 is not prime, of course, because it's 2 times 3, and these are not trivial divisors. And any composite numbers can be decomposed into a product of prime numbers. For example, 1, 7, 8, 3, 5, 6. That is 178,350 can be factorized as 2 times 3 times 5 to the power of 2 times 29 times 41. And 2, 3, 5, 29, 41, they are all primes. And you should check this is correct. Next, we define common divisors. Suppose A, B, C are non-zero integers. Non-zero integers. Then we say C is a common divisor of A and B. If C divides A and C divides B. So if both of these hold, then we say C is a common divisor of B, A and B. Here. Let's see an example. Consider negative 24 and 54. Then if we try to find the common divisors of these two numbers, we find plus minus 1, plus minus 2, plus minus 3, and plus minus 6. And there are no other common divisors. And you should note that these divisors all divide 6. Right? 1 divides 6, 2 divides 6, 3 divides 6. From this observation, we define the notion of the greatest common divisor. So suppose D is a common divisor of A and B. A and B. And also if all other divisors, if every common divisor D is just one of the common divisors of A and B. And every common divisor of A and B divides this D, then D is said to be a greatest common divisor of A and B. And we often use the abbreviation acronym GCD, or simply just without periods, GCD. A previous example, plus minus 6 is our greatest common divisors. And we usually take the positive one to say to call it as the greatest common divisor. Okay, and the positive greatest common divisor is denoted as GCD of A and B. So positive greatest common divisor of A and B. Okay. If there are we call it the greatest common divisor. This is because if there are two greatest common divisors, so if D and D prime both greatest common divisors, then this, according to the definition, since D prime is a greatest common divisor and D is a greatest common divisor is a common divisor, right? So D should divide D prime and D prime should divide D. So this means d is plus minus d prime. Well, you should prove this. So if this and this holds, then the only possibility is this. So the absolute value of these numbers should be the same, but only the signs are different. So therefore, we just pick the positive one and call it the greatest common divisor. Let's see a few examples. The greatest common divisor of 4 and 7 is 1. And greatest common divisor of 4 and negative 7 is also 1. And the greatest common divisor of negative 4 and 7 is the same as the greatest common divisor of negative 4 and negative 7, which are both 1. And another example, greatest common divisor of 6 and 4 is 2. And that is the same as the greatest common divisor of 6 and negative 4, and the greatest common divisor of negative 6 and 4, and greatest common divisor of negative 6 and negative 4. So the greatest common divisor of all these pairs of numbers, integers, is all 2. And another example, 616 can be factorized as 2 cubed times 7 times 11, and 1260 can be factorized as 2 squared, 3 squared, 5, and 7. So let's the greatest common divisor of these two numbers is 6161260 is so the common factors is 2 squared and 7. That is 28. And 616 can be written as 28 times 22. And this number 1260 can be written as factorized as 228 times 45. Okay, so this 28 is the greatest common divisor. And what about these factors, 22 and 45? Do they share any common factor? Actually, no, they don't. If they so the greatest common divisor of 22 and 45, and you should validate this, should be 1. No, if it's not 1, then that should have been included in the greatest common divisor part. Okay.